The last thing we have to understand is to figure out how to work with unbounded feasible regions. The idea for working with unbounded feasible regions is that we want to add artificial constraints that make it bounded. Here I'll represent the artificial constraints with the dotted black line. In this example, we have an unbounded feasible region, but if we added two artificial constraints, we can artificially make our feasible region bounded. This will introduce artificial corners. For our original feasible region, we had one original corner. Once we introduced the artificial constraints, here I use a red dot to signify the one original corner. To signify the three artificial corners that we introduced, I'll use a large black dot. We want to evaluate the objective function for all of these corners. After evaluating if an original corner is optimal, by optimal in terms of that maximum or minimum as specified by the problem, then that corner is the optimal solution. However, if an artificial corner is found to be the largest or the smallest of the evaluated corners, then we say the function is unbounded. Let's work through an example of this. Let's consider the problem where our constraints are as follows. X plus y is greater than equal to 4. Y is greater than equal to 0. X is greater than or equal to 1. And x plus 2y is greater than or equal to 5. Here, after graphing these inequalities, we see that we have three corners. Here our original corners are 1, 3, 3, 1, and 5, 0. To introduce artificial constraints, let's look at what the largest x value amongst our corners is. It's 5, so let's do one bigger than that and say x is less than or equal to 6. And in a similar fashion, we'll look at the largest y amongst our original corners. Here it's 3, so our new artificial constraint will be that y is less than or equal to 1 greater than 3, which is 4. We'll know that we chose correct artificial constraints if the artificial region is now bounded and none of the original corners were excluded. Here our artificial corners are 6, 0, 0, 4, and 6, 4. By choosing horizontal and vertical artificial constraints, finding those new corners is especially easy. I forgot to write them down before, but I'll write down the objective functions now. The first is to maximize 20x plus 30y, and the second will be to minimize negative 4,000x plus 2,000y. Our first corner of 1, 3 for our first objective function, 20x plus 30y, can be worked out to be 110. For our second corner, 3, 1, we can find it to be 90. and for our third to be 100. Actually, I was further mistaken. Let's say that our first objective function is to minimize 20x plus 30y, and our second objective function is to maximize negative 4000x plus 2000y. And here I see I'm riddled with errors. Our second artificial corner should actually be the point 1, 4. Our first artificial corner, 6, 0, would evaluate to be 120. Our second artificial corner, x equals 1, y equals 4, would evaluate to 140. Our third artificial corner, 6, 4, would evaluate to 240. Because we're trying to minimize our objective function, our optimal corner is the second original corner of 3, 1, which gives the optimal value of 90. Because this is an original corner, this will classify as an optimal solution for the objective function. Continuing to our second objective function, we can evaluate all of our corners. Our first one to be 2,000, our second one to be negative 10,000, our third to be negative 20,000. And moving on to our artificial corners, the corner 6, 0 would evaluate to negative 24,000. Our corner 1, 4 would evaluate to positive 4,000. And our third corner 6, 4 would evaluate to negative 16,000. Because we're trying to maximize, our largest value appears on one of our artificial corners, the corner 1, 4. This would correspond to that second objective function being unbounded. So to write down our results, first objective function of 20x plus 30y, where you're trying to minimize, has optimal solution 3, 1, and optimal value of 90. The second objective function, negative 4000x plus 2000y, which was a maximization problem, is unbounded.